Okay, welcome back. This video is about log properties, properties of logarithms. Ideally, I would like to keep your videos down to 20 to 30 minutes per day, and I know that you just watched a 17-minute video on compound interest, so I suspect that today we're going to go over a little bit, but in this video, we're not going to do a lot of examples. We're just going to kind of jot down the main ideas, and then in class next time, we will work a lot of examples. So in Algebra 2, you were introduced to logarithms. A lot of people think this is a very scary word and are really intimidated by logarithms, but let me just break it down for you. The word logarithm, if you break it down, loga or log comes from logos, and that basically means word. It's one of its meanings. And a rhythm, like arithmetic, pretty much means number. So in essence, we just have this scary looking word that just means number word. If you think of it like that, maybe you won't be so scared off by it. We abbreviate it for its symbol. We just say log, L-O-G. Where did it come from? So we've been talking already about logarithmic graphs and exponential graphs being inverses of one another. So let me just remind you about how we find an inverse. This is from our lesson on inverses we had back in December, I believe. So let's say you have an exponential function, just y equals a to the x. And let's say you want its inverse. To get the inverse of a function, remember you start by switching x and y. So that would be x equals a to the y. After switching x and y, the next step in the process is to isolate y, or solve for y. This is where we run into trouble. We don't have an algebraic method to isolate y. We couldn't use a root. We could try. It's not going to work. There's just nothing yet. So that's why mathematicians created something new, and they called it a logarithm. And what they did was they said, okay, let's put the base. So here we see the base a. Let's put the base down here. So log base a, it's a subscript. And then because with inverses you're switching the inputs and outputs, and in the exponential function you input the exponent, then for the inverse of that you would have to output the exponent. So that's going to have to be our output. So that's going to go over here. Oh, hang on a minute. What's our exponent here? It's y. So, oops, forgot to change my tool. So the output is y, the exponent, and so the x goes here. And that's how we write it. What it means is the base a, when raised to the power y, will give you an answer of x. So the input is the answer, the output is the exponent. So let's practice that a little bit. Here's our definition of logarithm, basically just a statement of what I was writing on the previous slide. You'll want to write that down. So if you need to pause the video, write that down and then resume, and we can go through these examples. All right, so let's practice converting from exponential equations to logarithmic equations. If I see 2 to the third equals 8, the base is 2. So in logarithmic form, I would write log base 2. Remember, my output has to be the exponent. So the exponent was 3. That goes over there. So then the 8 must go here. So log base 2 of 8 equals 3. And what that means is the same thing as the statement over here. It means take the base 2, raise it to the third, and you'll get 8. Let's do another one. 9 squared is 81. If you write that in logarithmic form, your base is 9, so log base 9. log base 9 of 81 equals 2. If you take 9 and you raise it to the second power, you get 81. We just kind of rearranged things a little bit. Let's work the other direction. If you're given a logarithmic statement like log base 10 of 100 equals 2, what that means is you take your base, 10, you raise it to this number over here, 2, and that should result in the argument here in the parentheses, 100. Similarly, if you take your base here, 3, and you raise it to the -1, you'll get the argument that's inside the parentheses, 1/3. Generalizing a little bit, if I have m to the p equals f, what's my base? M. I'm raising it to the p, so the p goes over here, and that will give me f. And then going the other direction, log base k of d equals z. What's my base? K. What am I raising it to? The z. What will that give me? The thing in parentheses, d. So the key to understanding logarithms is to understand this definition and be able to convert back and forth. When you see a logarithm, identify the base, identify the power, and then work your way around like that. Okay, let's look at some special notation. Just some reminders. This is all considered review because of Algebra 2 you had logarithms. Even though you're not expected to be an expert right now, you've seen all this before, so we're just bringing it back up into your mind again. If you see log of x with no base written in, it means log base 10 of x, and that is called the common log. So an example is if I see log of 1,000, I should think that it's saying log base 10 of 1,000. So to figure that out, I ask myself, 10, the base here, invisible 10, 10 raised to what power would give me 1,000? It would have to be the third power. So 10 to the third power is 1,000. And if you see ln of x, or natural log of x, it's equivalent to saying log base e of x. That's known as the natural log. We have common log and natural log. So if you saw, I usually use cursive on this for some reason, if you saw a natural log of e, what you would think in your mind is, even though it's not showing like this, you would think that it's saying log base e of e to the fourth. And then to figure out what that is, you would say to yourself, e, my base, raised to what power, goes over here, would give me e to the fourth. Well, I guess just 4. E raised to the fourth gives me e to the fourth. Now we're going to run through some of the properties of logarithms, and we're just going to do this briefly, and then in class we're going to do a lot of examples. So basic properties of logarithms. Log base a of a equals 1. For example, log base 5 of 5. What does that mean? It means if you take your base 5 and raise it to some power, which goes over here, your answer will be 5. 5 to what power? 5? 5 to the first power is 5. And that's going to be true no matter what number this is. 5, 10, 1 million. So I'm just calling it a. If those are the same, a raised to the first is going to be a. Next basic property, log base a of 1 equals 0. For example, log base 12 of 1. So think to yourself, take the base 12, raise it to some power, and your answer will be 1. What power must that have been? 12 to the 0 is the only way to get a 1. So no matter what your base is, if you take that base and raise it to the 0, you get 1. Now the base has to be positive, which is back here in the definition. The base has to be positive, and because of that, if you're taking a positive base and you're raising it to a power, you're always going to get a positive result. So the result x is also going to be positive. Okay, going back to where we were, looking at basic properties, the next two have to do with the fact that, as we learned about inverses, when you have f of x and g of x that are inverses, then f of g of x will equal x because the inverse operations will cancel each other, and g of f of x will equal x, same thing. So a logarithmic function with an exponential function inside it is just putting one thing inside its inverse. Everything's going to cancel but x. Or an exponential function with a logarithmic function inside it, assuming the base is the same. The logarithmic function inside the exponential function, because they're inverses, everything's going to cancel, just leaving x. So a numerical example of that would be something like log base 3 of 3 to the 11th is just going to be 11. Or 7 to the log base 7 of whatever, 39 is just going to be 39. You can even plug those in your calculator. You'll notice that you get those numbers. It's just the inverse functions canceling. So hopefully you're getting these basic properties written down in your notebook. And finally, we have three more properties. I've called them properties used to expand and condense logarithms. You'll recognize these from Algebra 2, but I'm sure you want some practice, which we'll do next time. We have the product property, the quotient property, and the power property. So go ahead, I know you can't see them all right now, but you can write down the product property and pause if you need to, and then I'll show you just a very simple example. So let's say we have log base 2 of 12 plus log base 2 of 9. That's going to be equal to log base 2 of 12 times 9, or 108. That property can be proven. Obviously, right now I'm just showing you the property, not proving the property to you. There's an algebraic proof of it. You may have seen it in Algebra 2. We're just doing a quick review. The next is the quotient property. Log base a of x minus log base a of y equals log base a of x divided by y. So if you're subtracting logarithms, you divide their arguments. The product property was if you're adding logarithms, you multiply their arguments. So an example of this would be, I could use the same numbers, log base 2 of 12 minus log base 2 of 9 would be equivalent to log base 2 of 12 divided by 9. And of course, we could simplify that fraction. Lastly, we have the power property. And the power property has to do with when your argument here has an exponent, a power, and this can be proven. I'm not going to do it right now, but you can bring that power out to the front. And you see it right here. The r is now multiplied by the log rather than it being an exponent. So an example of that would be if you had log base 5 of x to the 4th. It's equivalent to, bring the 4 down to the front, 4 times log base 5 of x. Okay, make sure you have all the important properties and definitions and things in your notes so that you're prepared for the notes quiz coming up next time, and we will run through a bunch of examples next time. Thanks.